Alright, I'm going to be covering some further mechanics in this video, specifically the chapter on the work energy principle. I think it's like chapter 2.3 or 2.4 in the textbook. I'm not too sure. But either way, if you do physics, then this topic should be fairly straightforward for you. All you really need to know about is like kinetic energy and potential energy. But there will also be a question at the end, which includes friction, so you'll need to know about that if you want to do the last question. Anyway, let's just get straight into it. So, some prerequisites before we get into any questions. We need to know that mechanical energy is the sum of all the kinetic energy and potential energies in a system. We also say that when no external forces, other than gravity, do work on a particle during its motion, then its mechanical energy is conserved. And the mechanical energy in a system also remains constant as long as the forces applied are conservative. And what that means is that work done only depends on its initial position and its final position. To give an example, if we had a particle at position A, and we say that some forces are applied, and it moves to a position B, then the forces are conservative if the work done is the same regardless of its path. So if the particle travels like this, or if the particle travels like this, then the work done is the same if the forces applied are conservative. And lastly, if the kinetic energy increases, then the potential energy decreases by the same amount, and vice versa. And this actually makes sense if you think about how we define mechanical energy. If our mechanical energy stays constant, and let's say we gain 5 joules of kinetic energy, then for it to stay constant, we need to also lose 5 joules of potential energy. And this works both ways. Alright, so now we can get into some questions. So we have a stone of 0.5 kilograms dropped from the top of the tower. So if we just draw a tower like this, and we have a stone, and it falls vertically to the ground with a speed of 12 meters per second. Okay. They ask us to find the kinetic energy gained by the stone. So if we're assuming that it starts from rest, which I mean, it doesn't say, but well, we just have to assume that, then its initial kinetic energy is just going to be 0, right? Because its speed is 0. So in this case, to find the kinetic energy gained, we just need to work out its final kinetic energy. So that's just going to be half times 0.5 times 12 squared, which is equal to 36 joules. For part B, we need to find the potential energy lost by the stone. And if we remember that mechanical energy stays constant, and that mechanical energy is equal to our kinetic energy plus our potential energy, then if we're gaining 36 joules of kinetic energy, we need to lose 36 joules of potential energy. And so we're losing 36 joules of potential energy. Part C, we need to work out the height of the tower. So we know that we're losing 36 joules of potential energy. And the only potential energy in this system is going to be our gravitational potential energy. And that has a formula of mgh, where we know the mass, and we know the gravitational acceleration. So all we need to do is solve for h. So if we do 36 divided by 9.8 times 0.5, we get h, and that is equal to 7.35 meters, roughly, to 3 significant figures. Alright, so in this next question, we've got a skier who's moving downhill at a speed of 6. Then they descend 50 meters, and then they ascend 25 meters. So their motion should look something like this, where they're falling downhill at a height of 50 meters, and then they rise 25 meters. And they start at point A, which is at a speed of 6 meters per second, and then they end at point B, which is at a speed of 4 meters per second. Right, and so we know the mass and the distance from A to B is 1,400 meters. Alright. And there's a constant resistance throughout this entire journey, which is 12 newtons. So if we calculate the work done by this constant resistance, that'll just be 1,400 times by 12, right? Because work done is equal to force times distance. And that equals 16,800 joules. And so, well, let's think about what this number actually represents. This number represents how much energy is needed for this entire journey to actually happen. So the skier needs 16,800 joules for this entire journey to happen. But remember that kinetic energy and potential energy are also doing work to sort of assist the skier in moving. Notice how their speed decreases and also their height decreases. So both their kinetic energy and their potential energy, or gravitational potential energy, both decrease. And that's because these types of energy are being spent for the motion to occur. So let's calculate how much kinetic energy and potential energy is actually spent in this journey. So to do that, all we have to do is calculate the change in kinetic energy and the gravitational potential energy. So I'll do half times 55 times 6 squared minus 4 squared. And that equals 550 joules. Then to calculate the change in gravitational potential energy, I'll do the mass times the gravitational acceleration times the change in height, which is going to be 50 minus 25, or just 25. And that equals 13,475 joules. So if we add up the total mechanical energy lost, that'll be 550 plus 13,475, and that equals 14,025 joules. And so this number represents how much energy is lost from kinetic energy and potential energy. But notice how, well, this number is lower than our number that we calculated here by the resistances. And that tells us that we need more energy for this motion to occur. So where's that energy going to be coming from? Well, it tells us in the question that the skier is actually doing work. So that energy is going to come from the skier. And if we want to calculate how much more energy we need, then we just need to subtract our energy that we calculated here by the total mechanical energy lost. So that's going to be 16,800 minus 14,025, and that gives us 2,775 joules. And so that's the answer. For our last question, we've got a plane which is inclined to a horizontal at an angle alpha, and they give us that tan alpha is equal to 3/4. So if I draw that out, it'll look something like this. And we're told that a particle is projected at point A with a speed of 25 meters per second. And so, using the principle of conservation of mechanical energy, they want us to find the speed of p, which is the particle, at the instant when it has traveled a distance of 25/6 meters up the plane. Okay, so we know its gravitational potential energy is increasing because it's traveling up a distance. It's traveling up the plane, which means that if we remember that our mechanical energy stays constant, then if it's gaining gravitational potential energy, then it needs to lose the same amount of kinetic energy. And so we can form an equation here where its final kinetic energy, if we call it half mv squared, is equal to its initial kinetic energy, which is a half times its mass times 25 squared, minus its gravitational potential energy, because the magnitude of its gravitational and potential energy that it gains is going to be the same as the magnitude of the kinetic energy that it loses. So we need to subtract by its mass times g times its height. And so, well, all we need to work out is the height at which it travels a distance of 25/6 meters. But remember, the 25/6 meters is at an angle, right? It's slanted like this. So if we say that's 25/6, and we got an angle alpha, then we need to work out the opposite of this right angled triangle. And that's going to be 25/6 times by sine of alpha. And sine of alpha we can find out because we're given that tan of alpha is 3/5, which means that its hypotenuse is 5 units. So sine of alpha is going to be 3/5. So its height is going to be 25/6 times 3/5, and that equals 5/2. So we can replace our height with 5/2. And notice how we can cancel out all of the masses. Well, we can divide by the mass. From here, all we need to do is solve for v. So if we multiply by 2, we get that v squared is equal to 25 squared minus 5g. And so v is equal to 24. The next part of the question only includes friction, and we need to find the speed at which it travels the same distance up. So the only difference here is that work is done by the friction, which decreases our kinetic energy, right? Because our gravitational potential energy is going to stay the same because it travels the same distance up. So all we need to do is subtract the work done by friction, right? I'll label it as W of F. And so to calculate the work done by friction, we need to know that the force of friction is equal to the coefficient of friction multiplied by the reaction force of the weight. And to do that, we'll need to calculate the weight that's acting on the plane. So if we draw the plane here with the particle there, then its weight is acting downwards, which is just mg, and the component of the weight, which is acting perpendicular to the plane, is going to act like that. And so we've got a triangle here, a right angle triangle, and this angle is alpha. So we need to work out the perpendicular component, and that's just going to be mg cos of alpha, which is going to equal 4/5 mg. And that's going to be our reaction force. So to find out our frictional force, we do 3/5 times by 4/5 mg, and that gives us 12/25 mg. But that's just the frictional force. So to calculate the work done, we multiply our frictional force by our distance. So we do 12/25 mg multiplied by 25/6, and that gives us 2 mg. And so all we have to do is subtract our work done by the friction in our original equation. And remember how we divided by m, the mass, and we also multiplied by 2. So we need to subtract 4g here. And that gives us a new speed of 23.2 meters per second. And that's the answer.